The universe is vast, but it is not entirely unknown. For centuries, we have been drawing a map of what is out there. We use the language of mathematics and the laws of physics. These tools allow us to predict what we should find in the cosmic dark. Our theories tell us how stars should be born. They describe how galaxies should form and grow over billions of years. This map is not just a guess. It is a detailed guide, built from countless observations and rigorous testing. It represents our best understanding of the cosmos. This framework has proven remarkably successful in explaining the grand celestial dance. This framework gives us expectations. We expect stars of a certain size to live for a specific duration. We expect galaxies to contain a predictable amount of dark matter. We expect planets to circle their parent stars in stable, orderly orbits. These expectations are not arbitrary beliefs. They are logical conclusions. The models we build are powerful. They can look back to the moments just after the Big Bang. They can also look forward, predicting the ultimate fate of our own sun and the Milky Way galaxy. Our cosmic map is a testament to human curiosity and intellect. However, the universe is not obligated to follow our map. It is the ultimate territory, and our map is just a representation. Sometimes, as we extend our gaze further into space, we find things that are not marked on our charts. We see objects that should be incredibly rare, or perhaps not exist at all. These are not monsters or miracles. They are simply observations that fall outside the neat lines of our predictions. They challenge our assumptions and force us to look closer at the map. These moments of discovery are the most exciting in science. They are invitations to deepen our understanding. An anomaly is a signpost toward a region of the map that is incomplete or needs redrawing. At the very edges of what we know, the next great leaps in understanding are born. These unexpected objects don't break science, they push it forward. They remind us that the universe is always more complex and more interesting than we can imagine. To understand why an object might be labeled as something that shouldn't exist, we must first appreciate how scientists build their understanding of the universe. The tools they use are called scientific models. A model is not a physical object, but a conceptual framework. It is a structure built from three core components: observation, physical laws, and mathematical logic. Observations provide the raw data: the light from a distant star, the orbit of a planet, the temperature of a nebula. These are the foundational bricks upon which everything else is built, collected through telescopes and probes over many generations. The mortar that holds these bricks together is our knowledge of physics. We apply fundamental principles like gravity, thermodynamics, and nuclear physics to explain the observations we gather. These laws are not arbitrary rules. They have been tested and confirmed in countless experiments here on Earth. By extending them into the cosmos, we can begin to make sense of celestial phenomena. Mathematics provides the language and the logic to connect these physical laws to our observations, allowing us to build a coherent and predictive picture of how a system works, from a single star to an entire galaxy cluster. From this carefully constructed model, scientists can then make predictions. If our model of star formation is correct, it should predict the range of masses a star can have. If our model of the early universe is accurate, it should predict the leftover radiation we see today as the cosmic microwave background. These predictions are the ultimate test of a model's strength. They transform the model from a simple description of what is into a powerful tool for anticipating what else we might find. It is a way of asking the universe a question and seeing if its answer matches our expectations. When a model's predictions are consistently confirmed by new observations, it gains our trust. It becomes part of the established map of our knowledge. This doesn't mean the model is considered absolute truth, but rather that it is a reliable and useful approximation of reality for a given set of conditions. It's this trusted framework that gives us a baseline for what to expect. This is why the phrase "shouldn't exist" has any meaning at all. It's a statement made against the backdrop of a successful, predictive model that has earned its place through rigorous testing and verification. The phrase "shouldn't exist" is really scientific shorthand. It doesn't mean an object is a supernatural phenomenon, or that it violates the absolute laws of logic. A star we can see clearly through a telescope obviously exists. What the phrase truly means is that the object's properties, its size, its location, its temperature, or its behavior, fall far outside the range of outcomes predicted by our current, most trusted models. It is an outlier, a statistical improbability so extreme that its presence suggests there is a piece of the puzzle we are missing, or a rule we have misunderstood. Imagine a model that predicts the maximum possible speed for a cheetah. This model would be based on observations of cheetah anatomy, muscle composition, and energy expenditure. If we then observed a cheetah running twice as fast as this predicted maximum, we wouldn't declare it a magical creature. Instead, we would recognize that our model must be incomplete. Perhaps there is a factor we failed to account for, or a biological mechanism we did not yet understand. The cheetah's existence forces us to revise our model, not to abandon our belief in cheetahs. The same logic applies to the cosmos. This deviation between prediction and reality is where scientific progress ignites. An object that shouldn't exist is a gift. It signals that our map of the universe, as detailed as it is, has a blank spot. It tells us that there is a new discovery waiting to be made. These anomalies are not failures. They are the engine of science. They compel us to ask deeper questions. Is the observation itself flawed? Is there a new physical principle at play? Or is our current model simply being applied outside of the domain where it is valid? The tension created by the unexpected is a creative force. Therefore, when astronomers speak of a galaxy that formed too early, or a planet that is too big for its star, they are not expressing disbelief in the object itself. They are expressing surprise that their well-tested frameworks did not anticipate it. This is a crucial distinction. It is the difference between doubting reality and questioning our interpretation of it. The existence of the object is a fact. The explanation for its existence is what is up for debate, and it is in that debate that our understanding of the universe expands and becomes more refined. In the grand architecture of the cosmos, we have a clear model for how planetary systems are built. They begin within vast, swirling clouds of gas and dust. At the center of this cloud, a star ignites. In the surrounding disk, leftover material begins to clump together. Gravity pulls these smaller pieces into larger and larger bodies. A chaotic, localized process of accretion eventually forms planets. That model predicts planets stay where they were born, in stable orbits around a star. A neat, orderly picture of celestial families bound by gravity. But the universe shows us exceptions. Astronomers are discovering a different class of world roaming the dark between stars. Rogue planets, untethered from any stellar system, drifting through the Milky Way alone. By our models, these should be exceedingly rare. Ejection requires a powerful gravitational disturbance, like a close stellar encounter. Such events aren't thought common enough to make many cosmic orphans. Yet observations are challenging that expectation. Using a technique called gravitational microlensing, where a foreground object bends the light of a more distant star, astronomers can reveal otherwise invisible massive objects. The method has revealed growing candidates that look like planetary mass objects with no nearby host star. Some studies suggest there could be billions, perhaps even trillions, of these rogue planets in our galaxy, outnumbering the stars. A staggering inventory our models didn't fully predict. The existence of so many forces us to reconsider theories. Are our models of planet formation incomplete? Maybe early solar systems are far more chaotic, forming many planets that get ejected. Or is there another mechanism that creates planets without a parent star? Perhaps dense pockets in stellar nurseries collapse directly into planet-sized objects. The lonely wanderers don't have answers for us yet. They are a profound, silent testament to a cosmic process we're only beginning to comprehend. When a massive star, many times the size of our sun, reaches the end of its life, it collapses under its own immense gravity and explodes in a supernova. What is left behind is one of the most extreme objects in the universe, a neutron star. This is a city-sized sphere of matter so dense that a single teaspoon of it would weigh 1 billion tons. Our models of physics, specifically our understanding of stellar evolution and neutron degeneracy pressure, predict the existence and properties of these stellar remnants. They should be hot, spin rapidly, and possess strong magnetic fields. But among the population of known neutron stars, a small and terrifying subset stands apart. These are the magnetars. While a typical neutron star has a magnetic field trillions of times stronger than Earth's, a magnetar's field is 1,000 times stronger still. This level of magnetism strains the limits of our physical theories. It could wipe the data from every credit card on Earth from halfway to the moon. It can distort atoms into thin needles and warp the fabric of space-time nearby. The existence of these ultra-powerful fields is a profound puzzle. Standard formation models do not easily produce such extremes. The dynamo mechanism would have to operate with unbelievable efficiency during collapse. It's like concentrating a refrigerator magnet's field to a level our equations can barely describe. Why this happens in some neutron stars but not others remains unanswered. We have observed them directly. They announce themselves with violent, high-energy outbursts. Stresses build in the magnetar's crust until it cracks, triggering a starquake. That releases a colossal amount of energy as X-rays and gamma rays. In 2004, a giant flare from a magnetar named SGR 1806-20, located 50,000 light-years away, was so powerful it disturbed Earth's upper atmosphere. These objects defy our sense of scale and challenge stellar models. The ancient giants, too big, too soon. Our modern understanding of the universe's history is encapsulated in the Lambda CDM model, the standard model of Big Bang cosmology. It tells a grand story of cosmic evolution over 13.8 billion years. In the beginning, the universe was incredibly hot and dense. As it expanded and cooled, matter began to clump, guided particularly by the gravity of unseen dark matter. This process was hierarchical. Small structures, like the first stars and tiny proto-galaxies, should have formed first. Over billions of years, these smaller building blocks would then merge and collide, gradually forming the larger, more massive galaxies we see today. This model of gradual, hierarchical growth is a cornerstone of modern cosmology. It is supported by vast amounts of evidence, from the cosmic microwave background radiation to the large-scale distribution of galaxies. The model makes a clear prediction. If we look back in time to the very early universe, we should see small, infant galaxies, not the fully formed giants that populate the modern cosmos. Looking deep into space is looking back in time, so our most powerful telescopes can test this prediction directly. We expect to find a cosmic nursery filled with small, messy galactic fragments and actively merging fragments. However, recent observations, particularly from the James Webb Space Telescope, are presenting a significant challenge to this picture. Astronomers are discovering galaxies in the early universe, just a few 100 million years after the Big Bang, that are far more massive and mature than our models predict. These ancient giants appear surprisingly well-formed, with structured disks and large populations of older stars. They look like they have grown up too fast, reaching a size and complexity that our models suggest should have taken billions of years, not a few 100 million. It's like finding a fully grown oak tree in a garden where you only planted seeds a week ago. This discrepancy has been dubbed the impossible early galaxy problem. These objects, by the numbers, simply shouldn't exist so early in cosmic history. Their presence suggests a fundamental tension with our established timeline of cosmic structure formation. For these galaxies to grow so large, so quickly, they would have had to convert the available gas into stars with an efficiency that seems physically implausible. Or the process of galaxy assembly itself must be much faster or work differently at early times than our current simulations suggest. These ancient giants are forcing us to re-examine the very first chapters of the universe's story. When an observation challenges a well-established theory, the first response is not to discard the theory, but to rigorously question the observation. This is the bedrock of the scientific method: verification. The initial discovery of a strange object is treated with a healthy, profound skepticism. The first question is always, is the data correct? Scientists immediately begin the methodical process of checking their work. They scrutinize every step, starting with the telescope's calibration and the software that processes the raw data, searching for any potential source of error that could mimic a real discovery. An anomaly in the instrument can easily be mistaken for an anomaly in the cosmos. This process of internal review is quickly followed by a call for independent confirmation. A single observation from a single team is never enough to rewrite a textbook. Other astronomers, using different telescopes on different continents or even in space, are called upon to look at the same object. This independent verification is crucial. If a different team with different equipment can replicate the finding, confidence grows significantly. It moves from being a potential fluke to a confirmed piece of evidence. This collaborative and sometimes competitive process of cross-checking ensures our knowledge is built on solid, repeatable facts, not singular, unverified claims. Peer review is another critical layer of scrutiny. Before a discovery is widely accepted, the paper describing it must be submitted to a journal. There, it is examined by anonymous experts in the same field. These reviewers probe the methodology, check the calculations, and evaluate the logic of the conclusions. They look for weaknesses, overlooked alternatives, and unsupported claims. This process is designed to be tough and unforgiving. It ensures only the most robust research becomes part of the official scientific conversation, filtering out mistakes and premature conclusions before they can muddy our understanding. This entire process, from instrumental checks to independent verification and peer review, is deliberately slow and conservative. It can feel frustrating in a world that craves instant answers, but its purpose is to protect science from its own biases and errors. It prioritizes accuracy over speed and certainty over excitement. It is this painstaking diligence that gives scientific knowledge its power and reliability. An object that shouldn't exist must first survive this gauntlet of scrutiny. Only then can scientists begin the exciting work of figuring out what it truly means for our understanding of the universe. We have journeyed to the fringes of our cosmic map, visiting a strange gallery of objects that, at first glance, should not be there. Lonely planets wandering the interstellar dark, stellar corpses with impossible magnetic fields, galaxies that grew to maturity while the universe was still in its infancy, mysterious visitors passing through our own solar system. Each of these discoveries presents a quiet challenge to our most trusted models. They are the outliers, the exceptions that test the rules we have so carefully constructed. They are the data points that fall far from the expected curve, demanding our attention and our curiosity. Yet, as we have seen, these objects are not a sign that science is broken. On the contrary, they are a sign that it is working exactly as it should. The scientific endeavor is not about confirming what we already know, but about venturing into the unknown. An anomaly is not a failure to be hidden, but a discovery to be celebrated. It is a gift from the universe. It is a signpost that points toward a deeper layer of reality we have not yet uncovered. Rogue planets, magnetars, and ancient giant galaxies do not invalidate the knowledge we have gained. They illuminate the path toward the knowledge we have yet to acquire. Skepticism, verification, patience, creative thought. It is the very heart of scientific progress. It is a process that exchanges dogma for doubt and certainty for curiosity. It builds its strength not on the infallibility of its theories, but on its willingness to revise them in the face of new, solid evidence. The story of science is the story of an ever-evolving map, redrawn and refined by generations of explorers who had the courage to investigate the places where the old maps were proven wrong. These objects are the modern-day equivalent of Here be dragons, not as a warning, but as an invitation. Therefore, we should not see these cosmic puzzles as a source of confusion, but as a source of profound opportunity. They are the friction that prevents our understanding from becoming static and complacent. They remind us that for all we have learned about the cosmos, it retains its capacity to surprise and to awe us. The objects that shouldn't exist are, in fact, the most valuable objects we can find. They are the engines of discovery, the catalysts for the next great leaps in our comprehension of the grand, silent, and wonderfully complex universe we inhabit.